Welcome to this segment of Kata training entitled Machine versus Exit Cycle Times. The principles taught in this video are based on content found in the Improvement Kata and Coaching Practice Guide by Mike Rother. The URL for that guide can be seen at the end of this video. Have you ever wondered why your processes don't produce parts at the expected rate, even when the machine cycles fast enough? You time the machines cycles are fine, but every hour the production board shows you getting further and further behind. That's truly a frustrating feeling. To understand why this happens, we need to understand the difference between machine cycle times and what we call exit cycle times. For example, we know that machine A's cycle time is okay because its red light comes on for 0.9 seconds each cycle. We've even charted it. The machine cycles are very consistent and well below the planned cycle time of 2.5 seconds that we need to meet customer demand. There must be something else going on. Perhaps something that we're missing. Let's time the machine again, but instead of timing the actual machine cycles as indicated by the red light, let's time the interval at which the parts exit the machine. We'll note the time when the exiting part reaches a specific point. These are called exit cycle times because they document the time between each exiting part rather than how long they are being individually processed. Charting these times show that the exit cycle times vary from part to part and that they're all above the planned cycle time. This explains why we can't meet demand. We're not exiting the parts through the process at a fast enough pace. Let's take the cover off of the machine and see what could be affecting how fast the parts exit the machine. We see that the part has to travel from where the machine processes it to the exit point. This takes a certain amount of time. Most machining operations have some amount of time needed for part travel. Variation in that time could be causing our problem. While we're watching the operation, we also notice that there is a periodic delay between when the machine cycle ends and when the part travel begins. We'll need to keep an eye on that delay as well. After our initial look at the process, we did some in-depth observations. The data on this clipboard shows the results. The data tells us that there is indeed some variation in how long it takes for the part travel to start after the process ends. We only saw about 0.2 of a second variation, but it is contributing to our exit time variation. We weren't surprised that our machine cycle times were consistently the same each cycle. Generally, you only see differences in pure machine cycle times when there is a significant difference in the material or amount of stock to be machined. Worn-out machinery can also cause issues with machine cycle times. Our observations did show that there is a greater amount of variation in the time it takes for the part to travel to the exit point. It seems to vacillate back and forth between 1.5 and 2 seconds. Each of the delays we documented contribute to the variation in the time it takes for the part to exit the machine process. As you can see then, it is important to keep in mind that machine cycle times tell us how fast the equipment is running, while the exit cycle times tell us the pace at which the product or services will exit the process. These times take into consideration all the other things that are happening both before, during, and after the machine actually cycles. Expressing this variation as a candle and wick might look like this. The top of the candle represents the lowest repeatable point. The lowest repeatable is that level at which we have seen enough exit cycle time observations to indicate that the process could operate at that exit cycle time if the variation was reduced. It's just an estimate based on a limited number of observations, but it is a good place to start. The top of the shaded area of the candle represents the actual machine cycle time. The wick represents the range of variation seen in the observed exit cycle times. We have seen that things happening within machines or operations can cause a difference between machine and exit cycle times. Now let's see why we need to consider the effect that the interactions of operators with multiple machines or operations can result in considerable variation as well. Here we see that machine A cannot proceed until the operator removes the part from the exit point. He must remove the part and physically carry it over and load it into machine B. Then he has to go to another location to perform a task before he can return to machine A for the next part. That next part may end up periodically waiting quite a while for the operator to return. Significant exit cycle variation can result when an operator is tending multiple machines that have different machine cycle times and which are not controlled through a single system. Adding more machines or tasks normally results in even greater variation. As we have learned, operator tasks and movement can add even more significant variation to the process. This increase in variation is reflected in both a taller candle and a longer wick. Measuring and charting exit cycle times, then, takes into consideration operator involvement, and it allows analysis and improvement. The more variation that you see in exit cycle times, the more you will probably see some or all of the following. Machines sitting idle waiting to be tended. An example of this situation might be in a cell in which the operator has two CNC lathes, one of which turns features on the front of the part, the other turning features on the back. There might also be a post-machining inspection in that cell that he has to perform for each part. In this scenario, the operator would unload the machine part and load an uncut part into the front cutting lathe. Then he'd hit the cycle start button. He would then blow the part off and move to the back cutting lathe, which he would unload and load. After he hit the cycle start button on that second lathe, he would have to move to the inspection station to do the inspection. After placing the part in a dunnage, he would move to the first machine to start the process over. If the machine cycle and task times were not carefully balanced, that front cutting lathe could have been waiting idle for some period of time, even though the machine cycle times seemed appropriate. Another scenario might be seeing multiple machines that periodically finish their cycles at the same time, causing wait time. This is particularly true in cells with identical machines that have been clustered together because of like operations. The final scenario for consideration is when you see cyclical or periodic external tasks or inspections that take the operator away from tending machines as they finish their machining cycles. To capture all the variation in the timing of the product or services coming from a process, time the exit cycles of that process. To do this, follow this procedure. First, pick an exit point at the end of the process. It might be when the product passes a certain point on a conveyor on its way to the next process, or perhaps when it's put into a container for transport. Next, stay at that point and wait for the next unit to reach that exit point. Using a stopwatch or app on your phone, start the clock when the unit passes that point. Hit the lap button every time successive units pass that point. If there are short interruptions in the flow of the units, don't stop timing. Capturing the length and timing of those interruptions in your process will provide the data you need to see how the process operates in real time. In most instances, time approximately 30 cycles, unless the cycles run so long that it is prohibitive for you to do that at that time. The more data points you capture, though, the more representative they will be of how the process operates. Now let's watch this timing process take place as it would in a busy cell that has a lot going on. Keep an eye on that exit point that we've chosen at the dunnage. We'll start the clock when the first part is placed in the dunnage. We'll be sure to focus on the parts as they reach that exit point. Try not to get distracted by all of the other actions taking place in the cell. As each part is placed, we will hit the lap button. We'll continue to do this for 30 points. It's interesting as we time these operations like this to note all the various things that we probably didn't notice before. We'll continue to watch the dunnage and hitting the lap button as we go. Next, we'll transfer the data points to a run chart. Be sure to draw the takt time and planned cycle time lines on the chart. Next, we'll find the lowest repeatable point that will become the top of our candle. Drawing a light line over the highest point gives us the top of our wick, and a line from the lowest data point determines the bottom of our wick. Remember that the top of the candle is a visual wave depicting the lowest repeatable point at which we estimate process can be run. And the wick represents the range of high and low variation we can expect to see in the process over time. Comparing these to the planned cycle time helps us understand whether we need to make improvements to the process in order to meet customer demand.